Ciao mi amigos! This video is a conclusion of a multi-part series on CFD for aerodynamics and Formula SAE. This video will cover the overall methodology of solving and post-processing starting from where we left off, which was just after setting the boundary conditions. And as always, before we get started, if you want to skip right to the tutorial, I will post the timestamp in the video description below. So picking up where we left off, we imported the Ahmed body into STAR-CCM and prepped the geometry and created a solution domain. Now we will cover the last two parts of CFD, solving and post-processing. Now that we have the solution domain generated, it is ready to impose physics on it to run the simulation. However, there are a few features we need to account for. Recalling the two main flows of fluid motion, laminar and turbulent, it's a safe assumption that our simulation will not be under laminar flow, so we need to go with turbulent flow. The kicker here is that there are multiple methods to model turbulent flow. The three main methods to model turbulence are direct numerical simulation, large eddy simulations, and Reynolds average Navier-Stokes. So in hindsight, kinetic energy of turbulent flow will eventually dissipate into heat. And how this actually happens is that large turbulent structures will branch off into smaller structures called eddies. And these eddies are fed from the foundational velocity of the larger structure. These eddies will branch off into smaller eddies and so on and so forth until it gets to the viscous level, which the energy will then dissipate into heat. So turbulent flow is famously governed by the conservation of mass and momenta of the Navier-Stokes equations. Direct numerical simulations, or DNS, directly solves for the Navier-Stokes equations from the large scales to the small scales. The problem is, however, directly solving for this requires an incredible amount of resources and computation time. Since, of course, we're directly solving for the Navier-Stokes equations. And the mesh itself needs to be incredibly fine. So because of this, DNS is only typically reserved for very small and simple geometries and/or turbulence studies. So the problem of computation time was fixed when we later found out that turbulence has an effect of thickening the fluid, making them more viscous than they really are. So in theory, we can modify the Navier-Stokes equations to mimic the effect of viscosity without actually having to resolve all the small eddies. This modification is called the eddy viscosity. That is added to the existing Navier-Stokes equations. This model is called the Reynolds average Navier-Stokes equations. This model is steady state or time averaged, meaning that if you take a flow and average it over time, the resulting flow will be your solution. This turbulence model is favored by industry for its resource and time saving abilities, as well as its overall similarity to DNS. This is what most of our simulations will be done under. So on one end we have DNS, which is the most accurate but most time and resource consuming, and on the other end we have RANS, which is the least accurate but least time consuming and relatively accurate. In the middle we have large eddy simulations. This is when we do take the time to resolve the eddies but leave out the smallest ones. This is done by effectively setting a low pass filter on the Navier-Stokes equations via a spatial and temporal averaging. Of course, a finer mesh is needed than a RANS model to solve the larger eddies, and so because of all this, it is still not used for practical applications, but more so in research. For example, you would use LES to do a vortex study and its effect from different geometries and etc. And so because of the wide practical use of RANs, we will use that turbulence model in our simulations. We will note that there are four submodels we can choose from in STAR-CCM: K omega, K epsilon, Spallard-Allamaras, and Reynolds stress. K epsilon and K omega are almost the same. Along with RANs, they account for history effects like convection and diffusion of um, turbulent energy. K epsilon, K for turbulent kinetic energy, and epsilon for turbulent dissipation rate, is shown to be more reliable with free shear flows with little to no pressure gradients, making them better for resolving solutions far away from boundaries or walls. K omega, omega for specific turbulent dissipation rate, succeeds where K epsilon fails, where the Reynolds number can be low and where the boundary layer is relatively thick and the viscous sublayer can be resolved, making them better for resolving solutions near the boundaries. It does run into the problem of not being able to solve far field solutions, unlike K epsilon. K omega SST, however, SST for shear stress transport, is special though. This formulation can switch to the K epsilon model when the flow hits free stream, effectively eliminating all the downsides of the two models with the upsides of both. Reynolds stress turbulence model is regarded as the most complete model of the four, disregarding the eddy viscosity hypothesis, and uses the exact Reynolds stress transport equation. This is the most accurate of the four. However, much like LES and DNS, it is more demanding when it comes to time and resources. Although still being not that much faster than the two, and so because of this, it's not widely used. Spallard-Allamaras is a one-equation model designed specifically for aerospace applications, and it has been shown to give good results for boundary layers subjected to adverse pressure gradients. However, for most aerodynamic applications, K omega SST is often preferred, and is what we will be using. Another important piece to solving is monitoring your residuals. A residual is the error between a measured variable to a reference variable. So in short, for CFD, a residual measures the local imbalance of a conserved variable in a controlled volume. So every single cell has its own residual, and the variables in question is the Navier-Stokes equations. A high residual indicates that there's large imbalances, while small residuals indicate that our equations are reaching a steady value. Therefore, we want small residuals for the instance that we want our simulation to obey conservation laws of mass and momentum. So after the simulation is done and we have our final solution, we can then move on to post-processing, where we can gather data from the sim. So there's no silver bullet for post-processing methods, since there are various applications of CFD, which will have different areas of post-processing interest. So it's really up to the user to obtain whatever data that merited a CFD simulation in the first place. So for us, we'll be looking at obtaining basic aerodynamic attributes such as lift and drag forces, as well as L over D, pressure contours, streamlines, and even center of pressure. All right, so without further ado, let's get on to the final task. So as always, we want to set the mood. I'm feeling cozy winter jazz. Okay, so starting from before, we have the geometry prepped and everything. We have the mesh already generated, as well as the boundary conditions inside of the region over here. So notice how we can't specify the boundary conditions. That's because we have to specify the physics over here. So before we do that, let's go ahead and hit record. So we have ham. So let's go ahead and make cheese. Okay. So let's go ahead and hit models. So because we're doing rounds, this will be a steady simulation. Gas. Okay, so when it comes to flow, this doesn't actually affect. This isn't pertaining to the flow itself. This is just like it's just the solver settings. And so for coupled flow, it takes more time and memory because it solves for the coupled equations for pressure as well as the velocities. Segregated is much faster, but coupled flow really helps with our residuals. So because we're in incompressible, we have constant density, and of course turbulent flow, as well as k omega. And we can see that SST is already selected by default. So now that we have that, let's go ahead and specify the boundary conditions for the velocity over here. So we want to make sure that we want to make sure that the velocity is normal to this boundary, and specifying it further, we're going to go ahead and travel at 21 meters per second, which is roughly about 46 miles per hour on the number. And so for the road, remember that we're trying to simulate a traversing road. So to do that, we have to for the tangential velocity specifications, instead of fix, we're going to go ahead and hit vector. For the relative velocity, we're going to go with the same as our inlet velocity, so 21 meters per second. And making sure, yeah, simple wall, traversing wall, the outlet, and for the pressure outlet over here, notice how this says 0 pascals. Now, this doesn't mean it's in a perfect volume. This just means that this is the gauge pressure. So when it says 0 pascals, that just means that it's atmospheric pressure. So now that we're done with our boundary conditions, let's go ahead and go to stopping criteria. And so I want to say this solution should converge before 1500 iterations. And now we can go and run some reports. So new report, we can go ahead and hit force. So to get the drag, we have to specify the directions going in. So it's at X. Then we want to specify the part inside of the region, not the part itself. So the armored body. And so this will be drag force. Make another one for lift as well. But instead of going into Z, going into X, it's now going to the Z. And of course, we're in pound force. So now, lift force. Let's also go with force coefficients. So this will be on the armored body. And because it's going in the X, this will be drag coefficient. Oh, I forgot to specify the armored body inside the region for the lift force. Don't forget to do that, of course. And force coefficients. So we want to go with our coefficient of lift. So specifying it in the Z. So now let's say like we want like a custom value like L over D. We can do that here by going on to definitions for expressions and then scrolling down to the report section. So we have L, so lift force, divided by D, the drag force. Specify L over D. And let's go ahead and create a monitor and plots from this report, as well as the lift coefficient and drag coefficient. So what this does is essentially as the simulation is learning, we can keep track of how it's behaving. Let's go ahead and create another scene for scalar this time. And let's go ahead and create the pressure contour. Well, sorry, the pressure distribution for our almond body. So the function of pressure. And perfect. Okay, so we're all set and ready to go. I just need you guys to now stop this recording and actually follow me really quick. So we have ham. And we also have cheese. So, this is an introduction to possibly the most powerful tool in CFD available, and that is scripting. Um, so, so, so STAR-CCM, much like any other computer program, it runs on a language, and that's all. And that's all denoted from the output, as well as the recording itself. So it saves all of our progresses that we made, and then converts it into a script file. So essentially, with ham and cheese, we can create a sandwich that is the beautiful marriage of the two. So let's go ahead and actually execute cheese. So let's go ahead and copy this. And paste. And let's rename this to ham. And let's go ahead and rename this to ham. And this to cheese. Okay. And we also have to include all the libraries from the solving. So we know that common and neo they are duplicates, and we can just get rid of them. Okay. So now so now that we have ham and cheese, we have now created a sandwich, or in this case, the sandwich. But in order to effectively say this, we have to name this script the same name as its public class. The sandwich. Alright, so let's say that, oh my god, I lost all my progress. What will I ever do? So with our new sandwich, we can actually run the entire process all over again, essentially without even lifting a finger, because I already saved the progress via the script. So if we load up a generic file, as we recall, or actually, I'll start from scratch. And meanwhile, this is loading up. I'll get back to you guys when it's done. Okay. So once again, we lost our progress. And went. Wait, we have nowhere to go. Well, as a matter of fact, we do have somewhere to go. We have the script. So let's go ahead and import our Ahmed body. And we're calling the first step, renaming the surface Ahmed body. And now play, or rather, input the script, the sandwich. No. Of course something went wrong with the sandwich. Oh, that's why. Silly. Okay. It only copied that one specific uh, line instead of the actual code. Okay, now we should be good to go. Import the sandwich. Now we can watch it run. Alright, everyone. So, as we can see, with a single click of a button, the script has now done and everything we did, and our simulation is now ready to run. So to run the simulation, you just hit the running man or hit Control R. So I will. You also need to initialize the solution. All right. So I will go ahead and run the simulation, and I'll reach back out to you guys when it's done. All right. See you. Hello, guys. All right. So the simulation ran, and I saved it, and so we can see that our residuals die down a bit, and then begin to oscillate near the end. Don't worry about this too much because our highest residual is going to be about 6 times 10 to the negative 6, which is well below our threshold, which is usually 1 times 10 to the negative 5. And even just by inspection, all of our reports seem to just they seem to plateau. So, as previously stated, there's a lot that goes into post-processing, and it's really up to the user to gather what they desire. So I will just introduce you guys with some of the tools of the trade. So from our reports, we can simply just tell it to run either of those values. That's by right clicking, and then a number should pop up there. And apart from the reports, you can get this a pressure distribution of the body, about what we expect. High pressure here, and lowers as it goes onto the sides and then stagnates. And we can also get a pressure sweep. Display. So let's edit our existing plane. Right, oh yeah. Perfect. Alright, so no displayer, just apply. And so now, if we go back to the scalar, we can add in plane section. And then we can impose a continuous pressure swoop. So let's see what that looks like at first. Okay, so we can tweak this a bit by start value, then going to 2 meters afterwards. So let's see how that changes things. Perfect. Okay. If we can change the cycle time, so instead of 10 seconds, we can do this in 5. And so to visually see the pressure sweep better, we can take out the element body. So now we're just focused on the actual sweep itself. So we can see that all these are jagged. This is because this is taking the values from the mesh cells themselves. So to smooth that out a bit, we can go onto the scalar portion and then hit smooth blended. And we can also select more points because, as you can see, this isn't the best gradient. That's a little bit better. So you can see the vortex forming around here, right there. Right there. There's a vortex. And so along with this, we can also gather the velocity of the specified region. So let me just edit this really quick. Oh, no turning. So you want this to be at negative 0.1. That way we can still see it. This will be like a pressure distribution about its midpoint, and then we can change the function velocity. So recalling that free stream velocity is about is 21 meters per second, and our prism layers go well past the threshold. It is a safe assumption that we have captured the boundary layer. We can also fiddle around with vectors as well by opening up a new scene, going to vectors, and then vector scene, vector 1, parts, main section, and give it a little animation for flavor. It is very chaotic, which is why we use streamlines. Now to obtain streamlines, we just go on to derive new part, streamlines, and then we select the element body. Give it a good hefty amount of points, and then hit new streamline displayer. For a second. In the meantime, let me go ahead and so you want to give it a function of velocity. Magnitude, and then give it another animation for flavor. We can see the vortex forming. And yeah, like I said before, um, oh, there's a lot to post processing. Um, and so, like, of course, like it's really up to the user to obtain what they desire that merited the simulation in the first place. I, this is really it. I wish this video was informative, and I wish you guys have a wonderful day.